Alright, silly people, here's the situation. We have a wave function that we need to normalize and then solve the Schrodinger equation using that for the potential energy. You need to find the expectation values of position squared, and momentum squared. Um, Find the standard deviations and see if it complies with the uncertainty principle. Um, so, I mean, you guys know how to normalize a wave function by this point, hopefully. It's just um, the integral over all space of the square modulus of the wave function, right? Should be equal to 1. So for this guy, the square modulus is going to be, you're going to have to take a complex conjugate of the wave function because it is complex. So it's going to be psi star psi, uh, which very simply ends up being um, exp, and then it's minus a mx squared over h bar. You have a minus I on this term, and then the same stuff, but with a plus I on this stuff. Okay. Um, so the imaginary components will cancel out, thankfully. You're just going to be left with a squared integral of exp minus 2amx squared over h bar dx. All right. This integral is of a certain form. Um, Generally speaking, the integral over all space of a um, exponent with an x squared power in it and a negative prefactor is going to have a solution where it's just square root pi over b. So throwing that in there, you'll just have a squared times the square root of pi h bar over 2am. Okay, and that should be equal to 1. So solving for a, you'll have 2am over pi h bar to the 1/4. Nice. We've normalized it. Now we need to use the Schrodinger equation to see what the potential energy is. The Schrodinger equation is going to read I h bar del psi del t is equal to minus h bar squared over 2m times the second derivative of the wave function with respect to position plus the potential times the wave function. All right. The wave function is a exponent. I'm just going to copy it down. The wave function is an exponent, so you'll just have to, whenever you're doing partial derivatives, you'll end up with the wave function at the end times the derivative of whatever was inside the exponent. If you're taking the derivative with respect to time, you have a minus ai on the t, so you're just going to have a minus ai times the wave function again. Then with position space, the first derivative is you just have mx squared over h bar times a minus a even. So minus 2amx over h bar times the wave function again. Okay. Then if you take the second derivative with respect to x, you'll have to do a little bit of power rule stuff. So minus 2am, or product rule stuff. Minus 2am at h bar. You'll have first times the derivative of the second plus second times the derivative of the first, which is just 1. We already know what the first derivative of it with respect to x is, so we'll just copy that down as well. So it'll be minus 2amx squared over h bar psi plus psi, and then factoring that minus sign through and factoring the psi out like that, you'll have 2amx squared over h bar plus or minus 1. Okay. Let's plug all that into the Schrodinger equation. So that's going to be IH bar times minus AI psi is equal to minus h bar squared over 2m times all of that junk. So just going to say 2am over h bar times psi times 2am x squared over h bar minus 1 plus v psi. The nice thing about how I've been doing it is that each of these now just has a factor of psi that we can cancel out, which reduces the work of the problem immensely. So let's simplify a bit more before we do anything else. We have minus h bar ai squared is equal to minus h bar squared. So it's just minus h bar a, because the two m's cancel out, one of the h bars goes away. And inside the parentheses, it's the same, plus v. I squared is minus 1, so this is positive 1 ha minus h bar a 2amx squared over h bar minus 1 plus v. Let's add the second term to both sides, so it's going to be h bar a times 1 plus 2amx squared over h bar minus 1 is equal to v. The 1's will cancel out, bam, bam. So you'll be left with h bar a times 2amx squared over h bar, which simplifies to canceling out the h's, 2a squared mx squared is the potential. All right. Now the expectation values. So expectation value of position will be the integral over all space x times the square modulus of the wave function. We already found what the square modulus was. It was just a squared exp times minus 2am x squared over h bar. So interesting to note that any integral over all space of the form x e to the minus some prefactor bx squared dx is always 0. Any integral of that form is 0. So this integral is certainly of that form, so the expectation value of position is 0. Cool. X squared, though, is a little bit different, so it's integral over all space x squared psi squared, which is going to be x squared a squared exp minus 2am x squared over h bar dx. I am going to have to plug in what the normalization constant is for this one, which, remember, we found it was 2am over pi h bar to the fourth, or to the 1/4, and it's the integral of x squared exp minus 2am x squared over h bar. This is also a standard integral. Generally, the integral over all space of x squared e to the minus bx squared dx, the solution to which is 1/2 square root pi b third. So just plugging that into our integral, yep, this is square root 2am pi h bar it's going to be 1/2 square root pi h bar cubed over 8a squared m squared. Okay, these are both the radicals now, so we can start to cancel out terms. The pi's will cancel out. You end up with an h bar squared left over. 8 divided by 2 is 4. You'll have, and these are both cubed as well, you'll have an a squared and an m squared in there. So you have 1/2 h bar over 2am, which is h bar over 4am. Nice. That's the expectation value of position squared. Now we better do momentum. So for momentum, the definition of momentum using Ehrenfest's theorem is just the mass times the time derivative of the expectation value of position, which we know to be 0, so that one's easy. If you want to do p squared, you're going to have to do the integral over all space of psi star, and then you use the momentum operator minus ih bar del x. You square it on psi and take the integral over a position. Taking the square of minus ih bar, you'll have a minus h bar squared. You're doing psi star del psi del squared psi del x squared dx. Okay, we have a form for the second derivative of the wave function. I'm just going to go grab that. Moving the prefactor out and distributing the negative sign will give you 2am h bar integral of psi star psi. It's 1 minus 2am x squared over h bar. We do happen to have a form for psi star psi, which is pretty cool, but we're not even going to use it. We're just going to say splitting this integral up into a integral of the square modulus over all space with respect to position minus 2am over h bar. You're just doing x squared square modulus dx, right? Um, recognizing the first term as the normalization condition, so that's just 1, and then the second integral will be the expectation value of position squared, which we already know. So I'm going to go grab that. It was h bar over 4am. And this guy. Simplifying a bit, cancel this stuff out, cancel out the a's and the m's there. 2 will become 4. You have 2am h bar, 1 minus 1 half, which is 1 half. So at the end of the day, you get ham. I'm gonna eat a snack after this. Finally, we need to look at the standard deviations for position and momentum and see if they comply with the Heisenberg uncertainty principle. That shouldn't be too bad now that we've calculated everything else. We got the standard deviation of x is going to be expectation value of x squared minus the expectation value of x squared, which this one was h bar over 4am. And then this one was 0. So it's just 1/2 root h bar over am. Sigma p then being p squared minus p squared is ham minus 0. So it's just square root of ham. Heisenberg uncertainty principle states that the multiplication of the sigma x and sigma p better be less than or equal to, or greater than or equal to, h bar over 2. So multiplying these guys together, you'll get 1/2 square root h bar over am times the square root of ham. The am stuff will cancel out. You'll end up with the square root of h bar squared. So it's exactly equal to h bar over 2. So it just barely conforms with Heisenberg uncertainty principle. All right.